Hi everyone. Okay, I'm back, and today we're going to be talking about antibiotics and getting into lab. So this is thinking like a research lab, like for undergraduates or precocious high school students. And I'm going to extol the virtues to you of working in a lab and tell you a little bit more about my regrets about why I didn't start lab sooner and things I could have done differently if I had another chance. Okay, so we'll start off with the first thing. So we're going to talk about antibiotics. So antibiotics are drugs that kill bacteria. That's essentially what they do. And bacteria colonize basically all parts of our body, especially the gut epithelium, like inside our GI tract. But they can really be found anywhere in your body. They're found on your skin, they're found in your, well, maybe not your eyes, because your eyes hopefully are sterile, although I'm not too sure. They can be found in your urine. They are generally, if they're found in your blood, it's a bad thing, but generally they just can be found everywhere in your body. And the talk nowadays is that antibiotics in general have become like less efficient at killing pathogenic bacteria. When I mean pathogenic bacteria, I mean bacteria that are able to cause disease. Like we have tuberculosis, we have multiple drug-resistant Staphylococcus aureus that's just floating around in the environment. It's colonizing normal people's just body, and the antibiotics that we have today aren't able to essentially wipe them from the body. So essentially, what I wanted to say was that antibiotics generally are a wonder drug. We've had them since World War II, the 1940s, where when they first came out, they were like, "Wow, we have this cool new drug that's actually been saving a whole bunch of people. We don't have to go back to the sanatoriums or like whatever outdated practices they were using. They were saving many lives, and essentially, this drug was like the one solution to bacterial pathogenesis, that is the cause of disease. Now, antibiotics have a specific spectrum that says, okay, this antibiotic is a drug that only kills this subset of bacteria, while this antibiotic is a different drug that works on this subset of bacteria. So the antibiotics work on different subsets of bacteria, meaning that you have to tailor it to the bacteria that you're trying to kill. Now, differences in bacteria include gram-positive, gram-negative, which essentially tell the person whether or not the bacteria has a big peptidoglycan layer or a small peptidoglycan layer. The peptidoglycan, the suffix glycan, just means sugar. So whether or not there's a sugar layer here, which actually determines a lot of whether or not a bacteria is bad for you or bad for your body. So antibiotics can be separated into a couple of groups by how they work. Some antibiotics are bacteriostatic, which means that they don't kill the bacteria. They just basically put the bacteria to sleep, and they just stop the bacteria from growing. And surprisingly, you would think this would be a smaller group of antibiotics, but this is actually a pretty large one. And this includes tetracycline, and that's one of like the most common antibiotics today. Alternatively, antibiotics can also be bactericidal, which means that they kill the bacteria, but they leave it where it's at. So essentially, the bacteria, this membrane stays intact, and the bacteria stays there but is dead. So you can still see the membrane there. And there's also bacteriolytic, which is the one that you would think of as like the mechanism by which most antibiotics act, although it's actually more of a rare case. And this would include like penicillin, amoxicillin, your beta-lactam antibiotics. Now, I'm going to tell you a little bit about when I was last semester in the fall. I was in MCU 112 here at UC Berkeley, and it's a general microbiology laboratory. And I was working alongside Matthew Traxler, and he is a dude that works with these really colorful bacteria called Streptococcus color. You can see the colors and the species name. And he looks for novel, new antibiotics because we are running out of antibiotics that are efficacious on other humans. So he goes in, he digs, he grows these bacteria in petri dishes, and he just basically looks for compounds that we could use as new antibiotics. And it's just a really cool guy. So it's just really great to be able to work with Streptomyces color. And like the people here at Berkeley are just like role models. I also took this bacterial pathogenesis class here, and It was led by two of my favorite instructors, Dan Portnoy and Russell Vance, and these two are like some of like the most famous people in the field. And so this is going to go a little bit into the lab part. I really wanted to work with Dan Portnoy. So this guy worked along Stanley Falco, and in case you don't know who Stanley Falco is, he discovered plasmids in bacteria, which I think is heckin' cool. Like that is one of the foundational concepts that like everybody knows today. Like bacteria have these little circular chromosomes that are inside that just float around and code for like secondary metabolisms or just like other things. But yeah, I just thought it was so cool. So I really wanted to work under Dan Portnoy, and he taught the class MCB 103 here, which is bacterial pathogenesis. And man, I studied, I worked hard, I tried so hard to do well in this class. And then I got my grades, and the finals were like, oh my god, I got a B. And I was like, holy moly. I tried so hard for this class. I wanted to impress this guy. I want to work in his lab. I'm a junior, so I'm like, time's running out. And I just didn't know what was going to happen, you know? So I talked to him, and he just like flat out rejected me. I sent him emails, and he flat out rejected me. So that was like, kind of like, oh my god. You know, like, sometimes things happen, right? So I was like, okay, maybe if I do well in this class, then maybe he'll give me a chance. So I get my grades back for the final and the midterm, and then I get a B, and I'm like amazed. I'm shocked that I got a B because I was like studying so long for this class, and I really wanted to impress this guy because bacteria is cool, you know. So essentially, what happens is I'm emailing him, he never responds, and then it turns out I got an A- in this class. I'm like, wow, this is my opportunity. But another professor, Professor Tago, which she taught another of my classes, microbial genomics and genetics, she was like, you know what, Joseph, I'll offer you a spot. And I was like, thank God. You're not as famous, you didn't work with Stanley Falco, but I think that, as an undergrad, you have to take every opportunity that comes to you. And, I'm not the greatest student. I don't study as hard as, the neurotic types, and I don't have like the genius capacity that some people do, but she works with vitamin B12 and nutrient sharing among different bacteria, and I think that's a step to start with. Like I don't have any experience with cloning, molecular technique, and really for these professors to take in an undergrad or these grad students or these postdocs to take in an undergrad, it's just a really difficult experience, I think, for them because they have to both teach and invest their time. And when I talked to Professor Taga, she was like, yeah, it's really quite difficult. It's only like the best of the best get in because they're recognized to have potential. But anyways, so I'm going to start that in the fall, and I'm really hecka excited to share my experiences with y'all on the channel. And Professor Taga worked with another cool lady. Her own PI when she was an undergrad was Bonnie Bassler, who I'll link in the channel description. But she was a heck cool lady. She studies how bacteria talk to each other and how they release these auto-inducer molecules into the environment so that they can know how many of their friends are there, how many of their exact species are in the environment, and also how many different species are in the environment so they can control group behaviors like virulence, like disease. And if we could find a way to curtail that, then maybe we would have a different way of attacking disease and solving it instead of antibiotics with bacteria that tend to wipe out entire ecosystems of bacteria, like we have this microbiota. So anyways, I just want to say that to those of you looking for research or started research early, if I had one regret, it would be that I didn't start research earlier, and I just really enjoy, the pursuit of the scientific truth. And next week, I'm going to be going to the QB3 boot camp here at Berkeley, and I'm going to dig my hands in a little bit with some molecular technique for people who have no experience. So yeah, to those of you looking, I just want to tell you, don't give up. And yeah, like in your free time, I have this really cool book that I got, Microbe Hunters, and this was like responsible for inspiring like a of the previous generation of microbiologists, and maybe it'll inspire you too. But anyways, that was my first video on this channel, and I just want to say thanks for watching. Bye-bye.